Since we've already learned about all of our rotational kinematics quantities and the equations that we can use to analyze rotational kinematics, let's talk about our last model for analyzing the motion of rotating objects. And that's going to be looking at these quantities, angular displacement, angular velocity, and angular acceleration in a graphical model. So all of these quantities versus time. So we already looked at all of these quantities in our turntable lab. You guys created these different graphs and started to look at the meaning of the slope and the area. So this video is really just to summarize what you should have discovered in that lab and just to really reinforce what meaning can we get from these kinematics graphs. What are the meanings of the slopes and the areas of these graphs? So as a review, we have these three standard kinematics graphs for linear translational motion. We have position versus time, velocity time, and acceleration time graphs. And there was a lot of information we could get from each of these graphs besides just what they specifically said. So as a review, a position time graph, if we take the slope of this position time graph, it tells us about the velocity of this object. So this position time graph starts with a negative slope. So that means we start with a negative velocity. But that slope decreases to 0, so that means our velocity decreases to 0. Then the slope of this graph is now positive and increasing, so that means our velocity becomes positive and increasing. Slope of position time gave us velocity information. And then from this velocity time graph, the slope of this graph gave us acceleration values. So the slope of this velocity time graph is constant and positive, so our acceleration is constant and positive. Then we could also look at the area between the graph and the x-axis. Starting with the acceleration time graph, the area between the graph and the x-axis right here specifically gave us the change in the object's velocity. Remember, this was change in velocity, not the overall velocity or final velocity. So this area is positive 4, and notice our velocity changes by positive 1, 2, 3, 4. Just keep in mind this area is your change in velocity, not your final velocity. Then the area under this velocity time graph would give us our change in position, which we call displacement. And this graph here is a nice reminder that areas underneath the x-axis are going to be negative. So notice for this first time interval, the object is moving backwards because our displacement is negative. And areas above the x-axis are going to be positive. This object is moving forwards. When we are looking at rotational kinematics graphs, as long as you understand those graphs from Unit 1, you already know how these graphs work. The slope of an angular position versus time graph, so theta versus time, is going to represent angular velocity. And the slope of an angular velocity time graph is going to represent angular acceleration. Notice it's the exact same pattern, just instead of looking at these linear quantities, we are looking at the angular rotational quantities. So these are the two slopes that have meaning for our graphs. Then on the other side, the area underneath the acceleration time graph, this angular acceleration time graph, represents change in angular velocity. And the area underneath the angular velocity time graph is going to represent change in angular position, also called angular displacement theta. So I do want to take a moment to go through a couple of examples simply because we haven't done these kinematics graphs in a while, but hopefully you're up to date on this information. So we have this graph which is specifically showing the angular velocity of a spinning object in radians per second. So this object is spinning and this graph is angular velocity versus time. Describe the motion of the object shown in this graph. So we really want to think about what's happening. Well, in the beginning, this object is spinning in the clockwise direction because it has a negative angular velocity and it's spinning pretty quickly. Then, for the first 3 seconds, it experiences a positive angular acceleration, and because of that negative angular velocity, positive acceleration, the object slows down and comes to an eventual stop after 3 seconds. But it only stops for an instant. It continues to maintain this positive acceleration and begins to speed up in the opposite direction until it is spinning at 6 radians per second, in this case counterclockwise because it is positive. So notice we can see this slowing down and then speeding up, but just mentally keep in mind that this is something that is spinning, not something that is moving in a straight line. So we know that this object is experiencing an angular acceleration because its angular velocity is changing, but what exactly is the value of this angular acceleration? Well, we can determine that from the slope of this angular velocity versus time graph. So you can use any of these portions. I'm just going to use this triangle here because it's really easy to see the change in y and the change in x. So slope is change in y over change in x. We are going to gain 6 radians per second, and this takes us 2 seconds. So our total acceleration is going to be 3 radians per second each second, specifically positive. So when is this spinning object momentarily at rest? So for a rotating object, it is going to be momentarily at rest when its angular velocity is going to be 0. That's going to happen at 3 seconds according to this graph. The next question is asking, what is the angular displacement, theta, of this object after 5 seconds? Now, the angular velocity of this object is constantly changing, so we can't just do velocity times time, but we can take the area underneath this graph. Now, this one's a good reminder that this area here is going to be negative, and this area here is going to be positive. So the total angular displacement is going to be the area of this triangle here, which is 1/2 the base, 3 seconds, times the height, -9 radians per second, plus the area of this second triangle here, 1/2 times the base, which is 2 seconds, times the height, which is +6 radians per second. Notice I decided to account for this negative area by just saying this triangle has negative height. You could say that this has positive height and just make the overall value negative. It's up to you as long as you know that overall this area is negative. So this first displacement is going to be -13.5 radians overall, and then the final displacement on this other triangle is going to be +6 radians. So -13.5 plus +6 is going to give us -7.5 radians. So this object is going to end up having rotated 7.5 radians in the clockwise direction overall. It's going to spin backwards, and then it's going to spin forwards, and it's going to end up 7.5 radians in the clockwise direction away from where it started. And the final question is probably the most challenging one, asking you to translate from one graph to the other. The one thing I didn't tell you was where this object started. I'm just going to assume it starts with a pretty positive angular position, just because the graph I gave you, it needs to move backwards first. So the only way it can move backwards on these axes is if it starts with a pretty high angular position. So I know this object is going to start off with a very negative angular velocity. So that means I want to start this graph off with a very negative slope. And over time, our negative velocity is going to get smaller. So over time, I want my slope to decrease until eventually my slope is 0 because the object is at rest. Then I'm going to begin to speed up in the opposite direction. So my slope is going to get more steep and positive. But one thing to note, I'm definitely going to end up behind where I started because we have an overall negative displacement. If I wanted a graph that was a little more specific than this, then I would have to give you more specific details like where the object started. But for now, we just want to remind ourselves of the general trends that we can see in these graphs. So as a final example, I've given you this angular position versus time graph. So I essentially want you to do the opposite of what we just did. More basic question, describe the motion of the object shown in this graph. What is it doing? Keeping in mind this is angular position, so mentally remind yourself this is spinning, this is not translating. All right, so I would describe this object as starting from rest because it appears that the slope of this angular position versus time graph is approximately 0. So in the beginning, it's not spinning. Then it is going to begin to spin, and it's going to spin faster and faster for about the first 7.5 seconds. It is increasing its angular velocity. Then it is going to spin at an approximately constant speed because the slope of this line is constant. And then near the end, it begins to slow down. It's going to rotate slower and slower till eventually it stops rotating because the slope of this line is 0. Its angular position is not changing at the end. And the whole time this object is moving in a counterclockwise direction because the slope of this line is always positive. Its angular position is always increasing, so it must always have a positive angular velocity, which is going to be counterclockwise for us. So hopefully this video was just a nice review of kinematics graphs. All we're doing is using slightly new variables and language, but the overall ideas are the same. You just have to get used to the new vocabulary and the new symbols. This should be a review because angular kinematics graphs work in the same way as translational kinematics graphs. If you need a deeper review of how these graphs work, I recommend you go back to Unit 1 and look at the wide variety of examples that we saw there.